Alrighty. Let me just get things up and going. All right, so hi everyone. As mentioned, my name is Sarah Thompson, and I am an undergraduate researcher currently in the BMAC lab. And today I'm presenting my project on characterizing morphology of collagen and elastin within the distal and proximal airways. And the BMAC lab is focused on understanding the biomechanics of the lungs. And a lot of the times people don't associate mechanics and mechanical engineering with our health and with our lungs. However, if you currently go to a doctor, a lot of lung pathology is actually highly reliant on mechanical measures. So when you breathe in and out, your lungs are kind of maintaining this perfect balance of stiffness and stretchiness. And when this goes wrong, it can actually lead to various illnesses. So a common illness characterized by excessive elasticity and overstretching of the alveoli of your lungs is a disease known as emphysema, which affects a lot of smokers because it's commonly caused by noxious gas exposure and actually affects approximately 14 million people in the US alone. So this mechanical measure helps us understand emphysema. And conversely, you don't really want your lungs to be overly stiff. Scarring and stiffening that can be caused by having repetitive pneumonia or even COVID-19 can lead to a disease known as fibrosis, which eventually leads to decreased lung volume and progressive respiratory and heart failure due to the lack of proper oxygenation. So it's really important for us to understand the mechanical properties of our organs and of our tissues. And however, current respiratory mechanics kind of lack a link between structure and function. So our lab conducts biaxial testing, which is where you essentially place a tissue into a machine that stretches it either axially or circumferentially. So then we can draw conclusions about how these tissues withstand stress and strain. Now, our particular regions of interest for my project are the trachea, which is the upper region of your airways, the large bronchi, as shown here, and the small bronchi. And the reason for this is because it was a longstanding belief that all throughout your airways that all these tissues behave the same mechanically. So they handle stress and strain in the same exact way because they're all lung tissue. However, our lab found that this is not true. The trachea, the large bronchi, and the small bronchi actually have different mechanical properties. And so we're trying to understand why exactly this is. Now, the first assumption would be, okay, it's the content, right? They're made up of different things. So in tissues, a super common protein of interest is collagen, because collagen is a crucial muscle protein that kind of enables the strength of your tissues. So our lab began by looking at the percent of collagen normalized to the dry weight of these tissues. And as you can see from the following bar graph, the trachea, the large bronchi, and the small bronchi actually showed no significant difference in the amount of collagen per dry weight. So although we're observing different mechanical properties, we couldn't say that it was due to the amount of this muscle protein. So the next assumption was, if it's not due to the amount of this muscle protein, maybe it's due to the shape of how these fibers are characterized. So that's kind of where my project comes in. And it's on whether or not mechanical differences in the airways are due to the shape of crucial muscle proteins. So I have two proteins of interest for this, and that is collagen and elastin. And as mentioned, collagen is crucial in maintaining strength of tissues, and elastin is kind of like its co-pilot. It also similarly is crucial for maintaining that strength of a tissue. So as you can see from the following images, there's a little bit difference in the overall morphology. So it's kind of hard to tell from the following images, but I'd like to point out there's kind of this waviness or curvature happening with the fibers. So you can kind of see it almost looks like there's waves within the trachea. Now within the large bronchi, you can see similar S-shaped curves, but it's not as pronounced. Now, where we saw a stark difference was within the small bronchi. The small bronchi, you might notice that these fibers look a little straighter and a little longer. However, as I mentioned, this is only observational. So my project then shifted to being able to actually quantify this and quantifying waviness as well as the orientation of these fibers. And all of my studies were conducted using porcine tissue. And so currently I'm undergoing a kind of 3-step process, which is fluorescent immunohistochemistry, then confocal imaging, and then using an algorithm developed by our collaborator, we are looking to quantify that waviness and that global orientation. So my current hypothesis is that the straighter collagen and elastin fibers will be observed in those stiffer regions of the airways. So the stiffer regions include that small bronchi I mentioned. And so intuitively, we think that that's likely due to the fact that those fibers are straight and stacked on top of each other, because intuitively, if you have a bunch of sticks stacked on top of each other, they're going to be pretty stiff to move. Whereas if you have things that have more of a curved pattern, there's a little more give and a little more room for that flexibility. So preliminarily, I have some images, and we were really happy to see that we observed similar trends to our histological study. So these are 40x images taken on a Zeiss 880 inverted microscope, confocal microscope, and the staining here is rabbit anti-collagen 1 with Alexaflor 488 to get this beautiful green color. And as you can see within the trachea, we have this similar trend of those wavy patterns going on with our fibers. Now, similarly, again, it's harder to identify within the large bronchi. You can tell that there is some curviness happening, but again, it's not really easy to make a concrete claim. And then lastly, within the small bronchi, again, we see these kind of flatter, longer fibers. So we were happy to see those trends, but we need to move on to quantifying them. Now, similarly, for this project, we were looking at elastin on its own for the first time. So we, again, observed similar trends, but the elastin, it's actually a little harder for us to actually see. With the collagen, the fibers were a little more pronounced. So we're going to be relying a lot on our quantification for seeing these differences in the elastin, because again, there is that waviness. There's some waviness going on in the large bronchi, and then in the small bronchi, again, we see those straight fibers, but we really want to see if this is quantifiable difference. So getting into what exactly that quantifiable difference is, currently the algorithm is a 2-step process. So right now it does the pre-processing using some MATLAB commands, and then goes through the software which actually does the calculations of that waviness and that global orientation. And for that, the pre-processing parameters are kind of the obvious things that you'd think of. So relative intensity, how bright does something need to be for it to be considered important and not an artifact, as well as the size of the fibers, the fiber thickness and the area. And then the circularity limit is kind of saying if something does a 360-degree circle, it's likely not actually a fiber. And then as well as image size. And then the software parameters for our calculation purposes include kind of the length of the fibers, the relative stiffness, and the maximum allowable waviness, as well as the maximal number of fibers and number of iterations per track fiber. So the way you can think of that is if we have all these fibers, what's the step size that we're looking at to kind of count the waviness and things of that nature within that fiber. So then it outputs histograms of our waviness and our global orientation. Now, this is kind of our preliminary testing with the algorithm, and the main focus right now is parameter optimization. So the issue that we're having right now is it's currently picking up some false fibers and some true fibers are being missed. So we need to vary those parameters to kind of limit that from happening. It's kind of hard to tell, but I can draw your attention to the small bronchi over here. This circular glob right here is actually a part of the cartilage, which should not be showing these collagen fibers. However, you see these lines right in here are counted as fibers, and they should not be. Now, conversely, within our large bronchi here, you might see some lines in the background that are faintly gray, and those should be included in the quantification and are not being included. So in terms of our future directions and goals currently, first things first is parameter optimization and making sure that we are limiting those errors. And then we'd like to conduct statistical analysis to assess if the differences in the global orientation as well as the fiber waviness is actually significant. And then since this study was done on porcine tissue, our next step is to look at it on a human sample. So we'd like to immunostain image and use this algorithm again to analyze the collagen and elastin within the human airway so we can make broader claims. And I'd like to quickly acknowledge Dr. Mona Eskandari and everyone in the BMAC lab, as well as Dr. David Carter and Dr. Mary Hammer, and Dr. Stanislav Polzer for developing this software, as well as Dr. Ernest Martinez and Rebecca Brown with the Marquee Star program. And with that, I'll take any questions.
Great, thank you so much. And don't forget, you can stop recording now, and yeah, we'll go into Q&A.